billions of records, fractions of a millisecond. In modern computing, waiting for a logarithmic search is no longer an option. The quest for constant time retrieval begins here.
Direct addressing is the theoretical ideal. An array slot for every possible key guarantees perfect big O of 1 speed. But to index 64-bit integers directly, you would need roughly 18.4 exabytes of contiguous memory. While less than global storage capacity, it is a catastrophic and impossible space-time trade-off for any single system.
To survive this trade-off, we use a hash function. This mathematical algorithm takes a key of any size, processes it deterministically, and maps it to a small, finite array index. It bridges the gap between infinite abstract data and limited physical hardware.
But mapping an infinite universe into a finite space invokes a harsh mathematical truth, the Pigeonhole Principle. If you have more items than containers, a collision is an absolute certainty. Furthermore, you do not even need a full table to encounter them. While it does not guarantee a collision itself, the birthday paradox demonstrates that the probability of a collision grows rapidly, reaching a high likelihood much sooner than intuitively expected.
The first defense against collisions is separate chaining. When keys collide on an index, we simply attach them externally using a linked list. It is robust, but if a malicious user forces many collisions, the system degrades into a linear search, crashing performance to big O of n.
To prevent hash flooding denial of service attacks, Java 8 introduced the Treeify strategy. Once a bucket receives its 9th colliding element, the table evaluates its total capacity. If the capacity is under 64, it simply resizes to spread the keys. But if the capacity is sufficient, the fragile linked list morphs into a self-balancing red-black tree, hardening the worst-case lookup to logarithmic time.
Linked lists cause severe memory fragmentation. High-performance systems prefer open addressing, an umbrella of strategies where all elements are stored directly inside the primary array. If an index is taken, the system calculates an alternative slot using a probe sequence. When implementing the specific linear probing variant, this forward scan rides the CPU cache at lightning speed.
While linear probing maximizes cache locality, it introduces a severe flaw: primary clustering. As slots fill up, they form solid blocks. New insertions hit these blocks and expand them further, creating a disastrous feedback loop when the table approaches capacity.
Open addressing also makes deleting data highly complex. If you simply empty a slot, you break the search path for colliding elements further down the line. We must leave a placeholder, known as a tombstone. Over time, the table becomes a graveyard of dead entries, slowing down searches until the system performs a full rehash to purge them and reclaim the memory.
To bypass these limitations, engineers deploy advanced algorithms. Robinhood hashing steals slots from the rich to give to the poor, equalizing probe lengths. Cuckoo hashing uses two parallel functions, physically kicking out older items to guarantee a worst-case constant lookup time.
Ultimately, there is no perfect dictionary structure. Your choice depends entirely on the hardware constraints. Do you need memory stability? Use chaining. Are you optimizing for ultra-low latency on a modern processor? Open addressing is your path forward.